calculating chemical quantities. In this video, we will explore the fundamental concepts of stoichiometry and how it is used to calculate chemical quantities. Stoichiometry is a branch of chemistry that deals with the quantitative relationships between reactants and products in a chemical reaction. It is an essential tool for chemists to understand the amount of reactants needed to produce a certain amount of product, or to determine the amount of product that can be obtained from a given amount of reactant. In this video, we will cover the following topics: the mole concept and Avogadro's number, balancing chemical equations, stoichiometric calculations using balanced chemical equations, limiting reactant and percent yield. Before we dive into these topics, let's first review some basic concepts of chemistry that will be useful in understanding stoichiometry. The mole is a unit of measurement used in chemistry to express the amount of a substance. 1 mole of a substance is defined as the amount of that substance that contains the same number of particles as there are atoms in 12 grams of carbon-12. This number is known as Avogadro's number, which is approximately 6.2 x 1023 particles per mole. The mole concept is essential in stoichiometry because it allows us to convert between the mass of a substance and the number of particles it contains. For example, if we know the mass of a substance in grams, we can use its molar mass, the mass of 1 mole of the substance, to calculate the number of moles of that substance. Conversely, if we know the number of moles of a substance, we can use its molar mass to calculate its mass in grams. To calculate the molar mass of a substance, we simply add up the atomic masses of all the atoms in its chemical formula. For example, the molar mass of water H2O is 18.2 grams per mole, which is the sum of the atomic masses of 2 hydrogen atoms 1.1 grams per mole each and 1 oxygen atom 16.0 grams per mole. Understanding the mole concept and Avogadro's number is crucial for stoichiometric calculations, as we will see in the next segment when we discuss balancing chemical equations. Chemical equations are used to represent chemical reactions. They show the reactants on the left side of the equation and the products on the right side, separated by an arrow. For example, the equation for the reaction between hydrogen gas and oxygen gas to form water is 2H2O plus OH 2H2O. The numbers in front of the chemical formulas are called coefficients and represent the number of molecules or moles of each substance involved in the reaction. Balancing chemical equations is the process of adjusting the coefficients so that the number of atoms of each element is the same on both sides of the equation. This is necessary because atoms cannot be created or destroyed in a chemical reaction, so the number of atoms of each element must be conserved. To balance a chemical equation, we start by identifying the elements that are present in the reactants and products. We then adjust the coefficients to ensure that the number of atoms of each element is the same on both sides of the equation. For example, in the equation for the reaction between hydrogen gas and oxygen gas to form water, there are 2 hydrogen atoms and 2 oxygen atoms on the left side, but only 2 hydrogen atoms and 1 oxygen atom on the right side. To balance the equation, we add a coefficient of 2 in front of the water molecule on the right side. 2H2O plus OH 2H2O. Balancing chemical equations is a crucial step in stoichiometry because it allows us to determine the mole ratios between reactants and products, which we will use in the next segment to perform stoichiometric calculations. Once we have a balanced chemical equation, we can use it to perform stoichiometric calculations. Stoichiometry involves using the mole ratios between reactants and products to determine the amount of one substance that is needed to react completely with another substance, or the amount of product that can be obtained from a given amount of reactants. To perform stoichiometric calculations, we follow these steps. 1. Write the balanced chemical equation for the reaction. 2. Convert the given quantity of one substance to moles using its molar mass. 3. Use the mole ratio from the balanced chemical equation to determine the number of moles of the other substance involved in the reaction. 4. Convert the number of moles of the other substance to the desired unit, mass, volume, etc., using its molar mass or other appropriate conversion factor. Let's look at an example. Suppose we want to determine how many grams of water can be produced from the reaction of 5.0 grams of hydrogen gas with excess oxygen gas. The balanced chemical equation for this reaction is 2H2O plus OH 2H2O. Using the molar masses of hydrogen 2.2 g/mol and water 18.2 g/mol, we can convert the given quantity of hydrogen to moles. 5.0 GH2O 1 mol H2O/2.2 GH2O equals 2.48 mol H2O. Using the mole ratio from the balanced chemical equation, we can determine the number of moles of water produced. 2.48 mol H2O 2 mol H2O/2 mol H2O equals 2.48 mol H2O. Finally, we can convert the number of moles of water to grams. 2.48 mol H2O 18.2 GH2O/1 mol H2O equals 44.8 GH2O. Therefore, 5.0 grams of hydrogen gas can produce 44.8 grams of water. In stoichiometric calculations, it is important to consider the concept of limiting reactants. The limiting reactant is the reactant that is completely consumed in a reaction, limiting the amount of product that can be formed. The other reactant is called the excess reactant, as it is not completely consumed and is left over after the reaction is complete. To determine the limiting reactant, we compare the mole ratios of the reactants from the balanced chemical equation to the actual mole ratios of the reactants given in the problem. The reactant that produces the least amount of product is the limiting reactant. Once we have determined the limiting reactant, we can use its mole ratio to calculate the theoretical yield, which is the maximum amount of product that can be obtained from the reaction. The actual yield is the amount of product that is actually obtained from the reaction. The percent yield is the ratio of the actual yield to the theoretical yield, expressed as a percentage. It is a measure of the efficiency of the reaction, with a higher percent yield indicating a more efficient reaction. Let's look at an example. Suppose we have 10.0 grams of hydrogen gas and 20.0 grams of oxygen gas, and we want to determine the theoretical yield and percent yield of water produced from the reaction. The balanced chemical equation for this reaction is 2H12 plus O2H12 all. Using the molar masses of hydrogen 2.2 g/mol and oxygen 32.0 g/mol, we can convert the given quantities of reactants to moles. 10.0 GH2 1 mol H2/2.2 GH2 equals 4.95 mol H2. 20.0 G/O2 1 mol O2/32.0 G/O2 equals 0.625 mol O2. The mole ratio of hydrogen to oxygen from the balanced chemical equation is 2:1, but the actual mole ratio of hydrogen to oxygen in the problem is 4.95, 0.625, which simplifies to 7.921. Therefore, oxygen is the limiting reactant, and hydrogen is the excess reactant. Using the mole ratio from the balanced chemical equation, we can determine the theoretical yield of water. 0.625 mol O2 2 mol H2O/1 mol O2 18.2 GH2O/1 mol H2O equals 22.9 GH2O. Suppose the actual yield of water obtained from the reaction is 18.0 grams. The percent yield is 18.0 GH2O/22.9 GH2O, 100% equals 78.6%. Therefore, the theoretical yield of water is 22.9 grams, and the percent yield is 78.6%. In conclusion, stoichiometry is a fundamental tool in chemistry that allows us to calculate chemical quantities and determine the efficiency of chemical reactions. By understanding the mole concept, balancing chemical equations, and performing stoichiometric calculations, we can gain a deeper understanding of chemical reactions and their applications in various fields.